Good evening, everyone. Let's start. Am I audible to everyone?
Yes, sir.
Okay, thank you. Good evening, everyone. Myself, Abhimanyu, and this will be the last interactive session for this course before your exam. We will be going through some of the problems where we have used like uh, two or three of the methods combined. First, let us go through a summary of what all we learned in this course. Initially we started with some of the basics of MATLAB. We learned how the program structure of MATLAB is, the for loop, if else conditions, and matrix operations, all those things. And then we looked at solving linear and nonlinear equations. We looked at the backslash operator. We looked at equations of like ax is equal to b, and then these are like linear equations. Then we looked at equations of type f is x is equal to fx, some function of x, which is like nonlinear equations. So we saw how to solve this using fsolve. Furthermore, we also saw methods such as Newton-Raphson. uh, for this nonlinear equations, we saw Newton-Raphson methods. We saw bisection method, second method, all those things. And furthermore, for the linear part, we saw one method using backslash operator where a is equal to x is equal to a backslash b. Then we also saw Gauss elimination and back substitution, all those things. Then we looked at differentiation, where we saw forward difference, central difference, and backward difference formulas. Then we went to integration, where we use the trapezoidal function, trapezoidal rule, Simpson's one-third rule, Simpson's 3/8 rule, and then some Runge-Kutta family of methods. Uh, During week 8, I think it was week 8 or week 9, we saw regression and interpolation. Uh, Here also we saw the least square. Here we saw for the regression part, we saw least square solutions. Mm, we saw we use the method. We first we wrote our own code for least square. Then we also saw LSQ nonlin, which also solves the least square solution for a nonlinear regression problem. Then we saw interpolation, where we saw p-chip and spline functions of MATLAB. And at the end, we saw differential equations part, where we saw the initial value problem, boundary value problem, PDs and DAs. We also saw mm, how to convert a boundary value problem into initial value problem, because all these solvers, OD 4, 5, and all those things, they move forward in time. So it's not actually converting a boundary value problem to initial value problem. Rather, we just change the time variable to some x or y variable, and we solved it as an initial value problem. Then we saw PDs and how to solve PDs using a method of lines, where we convert the PD into a set of ODs, and then we solve it. And further, in bonus part of weekend, we also saw the differential algebraic equations. Uh, so. mm in these topics, if any of you has any doubt, like for any in any of the topics, then we can discuss this. Otherwise, we can go through some of the problems, which where we are using one or two or more than two of these methods combined. Is there any doubt in these topics, least square, interpolation, regression? Furthermore, we will also be seeing some of these methods in the problems, but if you have some specific doubts regarding these topics, then we can discuss them first. Fine, then I will move forward. So yeah, so as I was saying, we will be looking at some problems where we have used multiple techniques. So the first one is the OD initial value problem, where we don't know the boundary condition at one, like we know the boundary conditions at the two ends, but we don't know the conditions at the one, like since it's an initial value problem, so we don't know the initial conditions at one end. Yeah, so if you look at this problem, this is a standard heat conduction through a rod problem. So we have a rod which is at ambient temperature. Just a minute. Yeah. So this is losing the ambient temperature we have considered as 25 degrees Celsius, and the rod is losing. Yeah. So this end is at 100 degrees Celsius and this end is 25 at 25 degrees Celsius, and we want to know the temperature distribution throughout this rod. Furthermore, the rod is losing heat to the surroundings. Okay. We are solving this as a steady state problem. Because the original equation, time dependent equation for this problem is something like del t upon del t is equal to del square t upon del z square minus beta t minus ta. So we are solving just a steady state solution of this problem. So we have assumed that temperature does not change with time, and we get this equation. So the way to solve this is that what we have done what we had done was that we converted this into we converted the second order ODE into two first order ODEs. So the one variable we assumed del t by del z as y, and then we get del y by del z as gamma t minus 25. Now we know that uh, t is equal to at z is equal to 0. We know that t is equal to 100. But we don't know the value of del t by del z, or the value of y at z is equal to 0. Like what ODE 45 if we are going to solve this using ODE 45, what ODE 45 does is that we need the initial condition. So if we are converting it into two first order ODs, so this is one first order OD, this is the second first order OD. So we need the initial conditions for both of these ODs. We know the initial condition for this thing. So at z is equal to 0, it's 100. But we don't know the initial condition for dt by dz. What's the value of dt by dz at z is equal to 0? Yeah, so the way we go around this is to use the shooting method. So we assume a solution for dt. We assume a solution for dt by dz at z is equal to 0, and we solve the problem, and then we try to find the value at t at z is equal to 1. Value of t at z is equal to 1, and then yeah. So if I try to solve this, so I start with some value of dt by dz. I might get some solution which is like this. So at x is equal to yeah, so this is x at x is equal to 1, and I know that this is 100. So at x is equal to 1, I know that my temperature should be 25 degrees Celsius. So if it's not 25 degrees Celsius, then that means that since this is fixed, we know this boundary condition, that so the only error with the solution is that we have assumed the wrong initial condition for dt by dz. So we again change this condition dt by dz, and then we again solve the problem. We might get some other solution, and if it's still off by off from 25 degrees Celsius, then we again change the condition, and we try to converge to we change the condition until we converge to a solution where the temperature at the end z is equal to 1 is 25 degrees Celsius. So there are various methods you can do this. One is like all the methods are called shooting method only because we are assuming an initial condition and then we are shooting the solution and then we are checking what end result are we getting. But how do we update the initial condition once we get the error? Once we calculate the error, which in this case would be the t that we are getting from OD45 at z is equal to 1 minus the t that we actual t that we are expecting at z is equal to 1. Now, how do we use this error to to update our dt by dz? That we can choose different methods. Like we can choose the second method, we can choose the bisection method, uh, we can choose some gradient method, things like that. So what I will be showing you is the bisection method. So bisection method basically means that bisection method basically means that suppose I take some initial condition and I try to solve my problem. So I was supposed to get a solution. Suppose if so I was supposed to get a solution. I was supposed to get a solution around this point. Uh, so I choose some point around here and then I calculate my fx. So if this x satisfies my solution, then my fx should be 0. Yeah, so let me make this much more clear. So this is my solution and this is my x1, and let me take some x another x. So this is my x2. Now if this x1 is the solution to my problem, like if x1 is equal to x all, then my f of x1 should be 0, which it is not, right? This is one initial guess. Then another initial guess, I take some value x2 such that my fx2 is less than 0 and fx1 is greater than 0. Now what that means is that if one point is one f of x is greater than 0, another is less than 0, that means that there is some point in between where fx becomes 0, right? So we need to find that point. How do we do that? We try to find a midpoint between these x1 and x2. Suppose that midpoint is somewhere around here, x3, and we then calculate the value of f of x3. If f of x, and then yeah, so we get some value of f of x3, and then we calculate we find the multiplication of fx1 and fx3. So if fx1 multiplied by of fx3, and then the other case is fx2 multiplied by fx3. Now if this sign, like the multiplication, is less than 0, that means that one of them is positive, one of them is negative. So that means that my solution lies between x1 and x3. So I update my x2 with x3 and then I again repeat this whole process. The other case is that fx2 is multiplied by fx3 is less than 0. That means that fx3 is on this side, like it's not on this side, it's on this side. And then I replace my x1 with x3 and the entire process repeats. Okay. So is this clear, or you guys have any doubt? We will see how to code this. Just a minute. Yeah. Okay. Shooting. Yeah. So I think it's visible. Okay. So this was our problem statement. we converted it into two ODEs. One is dt by dz is equal to y, and then the other one is dt sorry dy by dz is equal to this gamma t minus 25. Now I'm taking gamma as a 1. These two are my boundary conditions. So the first one, I know that T0 is 100. The second one is the target boundary condition. We want the next other boundary condition to be 25. So let me first go through the functions. So we have two functions in here. One is the ODE system itself. So this is simple. Dy by dt is equal to 0 is 2 comma 1. Dy by dt 1 is y2, that is t prime, and then dy by dt 2, that is del square t upon del z square is equal to gamma times y1 minus 25. It does not matter that I've written dy by dz, but you can write anything you want. It does not matter. And the other function is the solution of ODE for the solution of ODE 45. So it takes as input the this function takes as input two things: the boundary condition at x is at z is equal to 0, and the derivative at z is equal to 0. And then we, using these as initial conditions, I solve the problem ODE system using ODE 45, and then I return the temperature at the end at the z is equal to 1 boundary. Okay. Yeah. So we solve yeah, as for the bisection method. So yeah, so we need two initial conditions. Like for the bisection method, we need two guesses. Okay. Okay. Just a minute. Don't know why it's not open. Fine. So we need two initial conditions for the bisection method to work. So we will use one as that first boundary condition. We use that for the lower boundary as minus 150. We assume that dt by dz at the lower boundary is minus 150, and then at the upper boundary we choose the that it's minus 50. The other thing that we can, mm, yeah, let it be. Otherwise, we can choose something like because the temperature is going from 100 to 25 in 1 meter. So we can choose something like close to minus 75, something like that. Okay. Assuming that it's a linear drop, then we can choose something like minus 75. So the lower we can take as minus 80, and then the other one we can take as minus 70. Then we solve the problems at these two ends for these two conditions. Solve VBP for T0, T lower, T0, and DT0 upper. Uh, yeah, this is just a check that I'm doing so that I to make sure that both the points are not on the same side. So if like T and lower, if this multiplication is greater than or equal to 0, that means both the sides, both the points, both the initial conditions are on the same side. Like so if I choose 2 points like this, then that means that both the points are on the same side. So there is no 0 between these 2 points. So the program will return. It will not give you any output. Okay. Then these are just my tolerances. So I will stop if the error becomes less than 10 to the power minus 6, and I will run for 30 iterations. So this is I will calculate the midpoint first between those two lower and upper boundaries, and then I will solve the boundary value problem for this midpoint. I will calculate my error, and then I will just check if the error is less than my tolerance or not. If it's less than my tolerance, then I will break out of this for loop and I will end the program. Otherwise, I will again check for this condition, right? This condition. So here I am checking if it's greater than 0 so that both the points are not on the same side. Here I will check that if the condition is less than 0. So if T1 mid minus T end or T and lower minus T and target is less than 0, that means that mid and lower are on the opposite sides of the target. So I will update the upper end. Okay. So I will update this upper end with the TD0 mid, and T end upper will become T1 mid. Okay. Otherwise, I will do the opposite thing. And then this loop will continue until unless I get my absolute error less than tolerances. And then I will break out of this loop. Okay. So any doubt in the conditions? What we are doing, why we are doing? Okay, fine. At the end, I am just whatever the value I am getting for T mid, I'm running the simulation for that condition, and then I'm finally outputting the plotting the values. Okay, so I will run this. Yeah. So this is the solution that we are getting. You can see that the initial condition is 100 only, and at the end I'm getting y is equal to 25. Okay. What value of TT0 we got? We can check that using DT0 mid. So yeah, so finally it gave us a value of minus 98. That means that the linear approximation that we were initially suggesting, like minus 75, that was wrong because the solution is not linear in nature. Okay, so the final value we got was minus 98. So we can always choose some value around this. So like minus 100 or minus 90. It should run for those values also. Yeah. This time also it has converged to the same solution, minus 98.4776. Okay, so similarly, we can do this for any problem. We just need to change the ODE system, and everything else remains the same. Okay, if it's a second order ODE, we just need to change this function, and rest of the things remains the same. Also, we need to make sure that the two initial derivatives that we are giving, those are on the other side of the zero. Okay. Any doubt in this part? Fine. So still not done. So we'll look at the next problem. Yeah, so this is the same problem, but with a steady state, with a transient also. So we have already done this. So what we do is that we change this into we discretize this using central difference or any of the other methods. Usually central difference is preferred because it's much more stable as compared to backward and forward difference. And then we get a set of linear ODEs and we solve for them. So if I write it out, uh, that is square minus beta t minus t. Yes, so this will be valued from I is equal to 2 to n. Like if I am distributing it in n number of elements, so I will have n plus 1 number of nodes. So this equation will be valued from the second node to nth node. At n plus 1 node, at n plus 1 node, I will use the backward difference formula, and at n is equal to first node, the conditions are given to us, so we don't need to discretize for that. Or else if like in this case it's a what's it called, Dirichlet boundary condition. Yeah, it's a Dirichlet boundary condition at both the ends, so we don't need to discretize the n is equal to 1 at one node. But if it's a Newman boundary condition or a mixed boundary condition, then we can also discretize the n plus 1 node using forward difference method. Okay. So this is simple. This we have, I think we already have done this in week 10, I suppose. Yeah, in week 10, I suppose. So I will not be solving for this. I will be looking at some other problems. Any doubt in this method, differentiation and ODE initial value problem? Okay, then I will go to the next problem. The next problem is Newton-Raphson method with numerical differentiation. So this is like the solution. The problem that we are seeing right here is a simple problem. So we can easily find the analytical derivative for this problem, but sometimes you have like system of functions, a system of OD, system of functions where you don't where you where it's very difficult to find the analytical Jacobian of that system. So there the numerical differentiation is actually pretty convenient. First, we will see how to solve this problem using numerical differentiation. Then I will show you the general purpose Newton code. Yes, so let us first see the how to solve it using analytical method. So yeah, we will just create a function handle for the given function 2 minus x plus log x. And since it's a simple function, so we will create a function handle for the analytical derivative as well. And the initial guess is given to us as 1.2. And like we will assume that we will stop the solution once we get a error less than 10 to the power minus x, and we will solve for 20 iterations. Fine. So these are just like this is just a counting variable, and this is a boolean which I will be using to check if the solution has converged or not. So while not converged, that means while this is true and iteration is less than max iterations. So this is a negation symbol. That means that like right now my converged is false. So I will negate that, and that means it will become true. So while true, and this is also a Boolean operation, iterations less than max iteration. So right now iteration is 0. So this is also true. So both of these conditions are true. So the while loop will run. Okay. Um, yeah. Also, currently my x is the x naught, which is the initial condition 1.2. So I will calculate my fx and I will calculate my dfx using the function handles. And then this is my Newton-Raphson update formula. X nu is equal to x minus del fx by del fx. So in case of a multivariable, like a multivariable case, this will just become x nu is equal to x minus. I will have my Jacobian inverse here. So that means J inverse, and then that multiplied by f of x. So this f of x will be a vector here, so write capital X. This x will also be a vector, and this J would be a matrix, and this x would also be a vector. Okay. Yeah, this is a simple case, so you can easily write the analytical differentiation or the analytical Jacobian. But if it's like a system of equations, then you need to calculate the analytical Jacobian. Sometimes it's a 6 cross 6, like a 6 cross 6 dimensional system, 7 dimensional, more than 10 dimensions. So you have to write analytical Jacobian using hand for each of those 10 functions. You need to derivate and you need to find the derivative of that function with respect to every variable. So it's like a 100 cross 100 matrix. So it's actually very tedious to do that. So that is why numerical derivative is usually preferred in those scenarios. Yeah, so this is the Newton-Raphson update formula, and here I'm just checking for convergence. Absolute value of x nu minus x is less than tolerance, then converged is true, and I will display it. And this converged is so if you can see that I'm not using a break statement over here, or else I can just use a break statement which will exit out of this while loop. Otherwise I'm just changing this converged variable to true, and then I will update my x to x new and iteration to iteration plus 1, and then this will again check for this condition. But since it has become true now because I have changed my variable over here, so this will not enter the loop and it will exit it. Okay. Fine. So any doubt in this code? Okay, so I will run this. Yeah. So we are getting a value of 3.151462. The value is stored in X, so we can also check if it's correct or not. So I will just calculate f of x. F of f is this my function handle. So we are getting a value of close to 0. Okay, that means the solution is correct. Now we will do the same thing using numerical differentiation. So the first part is still the same. I will create a function handle with the given function. Rest of the things are same. Notice that we have one more parameter over here, h, which is the discretization parameter. How much I am discretizing for the taking the numerical derivative. Rest everything remains the same. I am calculating my function value. Then I am calculating my derivative using central difference. So f of x plus h minus f of x minus h divided by 2 times h. Okay. I can use even the forward derivative or backward derivative. I just need to change this line. Here I'm using central difference. And rest of the code is rest of the code remains the same. This is my Newton-Raphson update rule. This is convergence, and then this is the update for next iteration. So I will this. So right now format is short, so it's only displaying 4 digits after the decimal, and both of those 4 digits are same. So if we choose format long, then I run this. And I will run this also. Yeah. So you can see that I am getting the same result using both analytical derivative and the numerical derivative. Okay. Fine. So I was supposed to show you this for. Let me see if I have that function with me right now. Is that function? I hope you can see my screen. So this is a vehicle bicycle model. So like it's a vehicle dynamic model. So we are assuming that the vehicle model is replaced by a bicycle. The equations of this system are the system equations. Yeah, so these are the equations of that system. We have it's a 5-dimensional system, 3 dimensions from the vehicle dynamics and like from the vehicle longitudinal dynamics, lateral dynamics, and the yaw dynamics, and 2 for the tire dynamics. So you can see if I try to find a analytical Jacobian of this system with respect to these three variables, then it's very tedious. It's a very tedious thing to do. Like all of these fx, fy, these are all dependent on. I think I have not mentioned over here. Yeah, so all of these fx, fy, all of these things are dependent on vx, vy, omega, and uh, small omega and capital omega. So it's like a very cumbersome equation that we get finally out of it. Hope you can. Yeah. So you see, these are my tire equations. And then inside this alpha, I have some more equations. Yeah, so these are my equations for alpha. They are dependent on Vx, Vy, and they are dependent on Vy, gamma, and Vx. Then Fx is in turn dependent on gamma, and then all of these three states are dependent on Fx, Fy, right? So if I try to find a analytical Jacobian of this system, it's very tedious thing to do. But why do I need to calculate the Jacobian? Because I want to find zeros of this system. Like I want to find a fixed point of the system. Of what is a fixed point? A point where x dot is equal to 0. Right? So all of these states are there, right? Vx dot, Vy dot, omega dot, and omega I dot. So I want to find the value of these Vx, Vy, omega, and omega I where these derivatives become 0. So I'm basically trying to do a nonlinear root search only in multi-dimension, right? For multi-variable case. So in such situations, usually a numerical Jacobian is much more preferred. That is what also I am doing over here. So this is the part where I'm calculating my numerical Jacobian. I am trying to evaluate my function at some point, and then I am trying to perturb that point by a small amount, only in a given direction, right? Uh, let I'm just trying to find a function where I can show you this exactly. Uh, yeah. So let us create a function. And some other function. Let me take a simple case only. Okay. I don't know if the solution to this problem exists or not, so we will just check. So we will use this Newton-Raphson code. The first one is that I'm just calculating my size of my unknown vector. So in this case, that would be 2 cross 1. Like whatever here x is the initial condition that I'm giving. So this will be just like if I'm giving a 2 cross 1 vector of initial conditions, that means I'm solving for two variables. Epsilon is just a small perturbation that I will be giving. Okay, let me go back to my iPad so that I can explain this to you better. Yeah, so usually what we do is that our update rule is x nu is equal to x minus j inverse and f of x. Now the only difficulty that we have is in calculating j inverse, because fx is usually simple to find. X is we already know that x nu we can find with that. The only difficulty is to find the j inverse or to find the Jacobian. How do we usually find it? So we know that Jacobian is del of it's a multivariable case, then del of f1 with respect to del x, del of f1 with respect to del y, del of f2 with respect to del x, del of f2 with respect to del y. I'm just telling you for a 2 cross 2 case. So what do? We usually just add one more matrix to it. Uh, yeah, function f equals x plus perturbation the perturbation. Yeah. So first we evaluate this part. So how do we do that? Uh, we just simply take del of we just simply calculate f of x minus f of x minus h, or else we can this is like backward difference, and then we divide it by h. We do this for one part. So that means that for j 1 comma 1 this is the case. For j 1 comma 2, sorry, it's a multi-dimensional case, so that means it should be x comma y, x minus h comma y, x y, x y minus h on h, and similarly for 2 1 and j 2 2. Okay. So we do this and then we do this for the number of elements that we have in the Jacobian. Like if it's a 3 cross 3 system, then we do this the entire process 9 times, and like that. Okay. How much do we perturb it? We just perturb it in this case I was taking h is equal to, what was the value of h that I was taking? I was taking h is equal to 10 to the power minus 5. Yeah. So we just perturb it by a small amount. If I perturb it by a very large amount, 10 to the power minus 2 or 10 to the power minus 3, and then the numerical Jacobian would be very far off from the analytical Jacobian. Okay, because this step size is very large as compared to this small size. So usually we take sizes in the range of 10 to the power minus 6, minus 5, minus 8, like that. Very small sizes. Just make sure that you are not getting any round of errors creep into the Jacobian, and you are fine to go. Okay. Yeah. So that is what I'm doing in this code. Okay. Was my tablet screen visible to you guys? So any doubt in this part, the numerical Jacobian, how we are calculating that? Is this part clear to you guys? So we have this Jacobian which we want to calculate. How do we do that? We perturb it like so. We have four elements in here. For each element, we perturb one part of the function. So for the first element of the Jacobian, we perturb the x part of the function f1, and then for the second row of the Jacobian, we perturb the mm, x for the second row first element, we perturb the x part of the function, and for the second row second element, we perturb the y part of the function. And likewise we do for all the elements of the Jacobian. If it's a 3x3 system, then we do it for all the 9 elements. And likewise, how the size increases, this calculation also increases. Okay, so I will now explain the code. Yeah. So what this Newton-Raphson is doing, if you look at this loop, so D here is my Jacobian, and I'm calculating for the first row. So for the first row, I'm evaluating my function at the value of x plus this perturbed part. So this perturbed part is basically my perturb matrix is a identity matrix. So right now I'm just perturbing one element of it, the ith part of it, and then I will be then I divided by epsilon. Epsilon is very small number, so that this is basically my h value. Okay, so very small h value. uh, ee is my the fun- my is ee is my current function value at the x value, like without any perturbation. So e is my f eval function at the x value, and then this part is the perturbed part, and I'm subtracting those two together and dividing by h. So basically this is a forward difference method that I'm utilizing over here. So I do this for all the parts of the all the rows of the function Jacobian, and then this is my Newton-Raphson update rule. Okay, d inverse multiplied by function, in this case e. Okay, rest of the things are same. So this will continue to run until my norm of EE is greater than 20, multiplied by max norm of x is greater than 10 to the power minus 10. This means that if either of those two is in the range of 10 to the power minus 5, it will run until that, or my number of iterations is greater than n max. Okay. Yeah, so I will try to solve this function using this Newton method. So I just need to input my function and then the initial condition. I don't know if this is solvable or not. So I'll just try to input some initial condition. 0 is not defined. 2. I don't think this is solvable, but let's see. Okay. Let me save this function over here. Yeah, so it did not converge. I don't think this problem is solvable. Um, yeah, it's not converging. We will just look at a simple function. Yeah. So you can see that this 2D problem, we solved it in 7 iterations, and the solution that we are getting is for the first equation, f is equal to pi, which is like it's the same function that we are using over here, 2 minus x plus log x, 2 minus x plus log x, and then 5 minus 3x by 2. So the for the second, the solution is 1.666. Okay. So it gave us the solution in 7 iterations. This the code that we have written over here. This is like for the single function, for single variable, but this Newton code we can use for multivariable. So I can increase this function to 3 cases. Can add one more condition over here. Also, I can just make this a bit more interesting. I don't know if this will solve this or not. Yeah, still it is solvable. We can add n number of variables in here. We just need to so now it's not converging, probably because of the sign. Uh, Still not converging. You need to choose like the function needs to be something which can be solved. I'm just entering numbers in here. So for simple cases, it does work. So any doubt in this Newton function? So multipurpose function that you can use for any number of variables you want. Okay. Any doubt in this? Uh, Fine then. So I will go to the next part, which is fitting the finding the basically finding the numerical derivative for experimental data. So this is like a bunch of data that is given to us. For the this column is temperature. These are the ideal values that we should be getting, and the third column is the experimental values that we are getting. Now we want to find the derivative of this function for these values. Okay. So you can see the ideal. This is the ideal values what we should be getting, and the red dots are the experimental values that we are getting. Now, if we calculate the numerical derivative, then we are bound to get large errors because, compared to this, this is like off here, and then this is off here, this is off here, this is off here. So we are bound to get large errors compared to the what we are supposed to get. Okay, so if we do that, this is the I pressed the timing button. So first, let us run this first section. Yeah. So this is the ideal data that we are supposed to get, and this is the experimental data. Okay. Now, if I calculate my derivative using central difference only. So Mm. So first one is the experimental values. The next one is the real values. So you can see that the first one is not that off. Yeah. So for the first one, the difference is not that much. This one is around on the line itself, and this one is away from the line. So for the first derivative, we get a good approximate for the experimental and the real value. For the second derivative, this is on that side of the line, this is on this side of the line. So we get a way of estimate for the second derivative. Third derivative is likewise closer. It's not correct, but it's closer, because like these 2 points are pretty much on the same pretty much the same distance from the from the ideal curve. Okay, so that is why this difference is very less. And likewise for this point is closer to the ideal, and this is also like a bit off. So we get some error over here, but it's a small error. Okay, so this is like the values that we will be getting from the errors that we will be getting using experimental data directly without any filtering or anything. Okay. Now, what people usually do is that they filter out the data and then they calculate the numerical derivatives, or they sort of fit a curve. Fitting a curve is also like you are removing the high frequency content from the data. Okay, and then on the low frequency content you are doing your analysis. So that basically was curve fitting basically does that only because if some point is, suppose I have some line like this, right? Now I want to fit a curve through this. So basically, it also depends on the degree of polynomial or the type of curve that you want to fit. But usually you will get something like, you will fit something like this to this line, to this curve. Okay, if you fit a line to through this set of points. So this line is basically a filtered version of this data. We have removed the high frequency components, like the components that are those the components which were giving these abrupt changes in the values of this data. So we have filtered those content and we get a smoothed out version of this data. Okay. Likewise, if we fit if we join these points together, so we get something like this, right? But if we try to fit a straight line through this point, through this data, then we might get something like this, which is much smoother version of this jagged line, right? So that is what we usually do. We fit a curve through that data, and or we use a low pass filter through that data, and then we do our analysis or we do our calculations on that filtered data. Okay. So in this case, we are just going to fit a curve through this data. So we will be fitting a polynomial, second degree polynomial to it. So I think I have a slide for that. No, I don't. So what we do basically, we create that so this is our method for fitting least square fit to a data. For our case, we are trying to fit a second order polynomial. That means this u1, u2, u3, that this becomes t1 square, t2 square, t3 square, like that. x1, x2, xn becomes t1, t2, and tn. One remains one. We don't have this third w variable, so this will not be here. And then this is like only three variables, so a0, a1, a2, and these are all the known points. Okay, so all the r values, experimental r values. Okay. So we create this X matrix, which for our case would be a 6 cross. I think there are 6 data points. 1, 2, 3, 4, 5, 6. Yeah, which for our case would be a 6 cross 3 matrix. We take this transpose. Take this, do this multiplication. We get a 6 cross 6 matrix. We take inverse of that and we multiply it by X transpose and then multiply by Y. Okay. So this is what we are doing over here. We are creating first the X matrix. Y matrix, we have just taken the R experimental values, and then we do this least square solution of for phi, and we get the equations for the we get the coefficients for the second order fit to this data. Okay. Yeah. So let us also plot this. Plot. Stable T naught. Plotting T by T naught with respect to our fit. Okay. Yeah. So this is the yellow line. It's a second order fit to through this data. So you see the initial line which was like this. Now we have a much smoother line in place of that, and now we will be using this line to calculate our derivatives. Okay. So this is what we are doing over here. Since we have fitted a second order curve, so we already know what our derivatives would be. It would be like a naught plus 2 a2 t by t naught. Okay. That is what I have done over here. We are calculating our derivatives only at only at the given temperatures t by t naught, and then I am displaying the results. So these were the results that we were getting using the experimental data and the real data. Using the experimental data without the curve fitting. So now you see, this is a fitted data, not a experimental data. Okay. Yeah. So for the first curve, we see that the error has increased compared, like instead of decreasing, because this point has even moved that side, and this point is also moved this side. So overall, we have an increase in the distance, right? So that is why this error has increased. But for all the other values, all the other points, we see that error has decreased, because all of these points, it's much like this point is much closer to the blue line as compared to the red point from the blue line. Similarly, this point is much closer to the blue line compared to this red point, right? And this last point, it's approximately on the same point as the blue line, right? So for the second, third, and fourth point, we see that the error has decreased compared to the experimental data, right? Yeah. We can even do a third order curve through all these points, and we can see how much, what sort of errors we are getting. It's up to you. Like you can choose a number of points, different number of things, different number of curves, even a sinusoidal curve like that, and you can see how what sort of fitting you are getting. And then if you are satisfied with that fit, you can check your R score, and then if you are satisfied with that, then you use the desired fit to do all the further calculations. Okay. Fine. So any doubt in this, on the curve fitting? Fine. So I will just take this last example, and then we will solve two problems. Mm. Yeah, so this is a PD in multivariable. Last week, or I think in week 10, which week was it? Yeah, in week 11, last week only, we saw PDs, how to solve PDs. So last week we saw how to solve PDs, but we only did for single variable. We did not solve for multiple variables. So this is one example for that. The solution methodology is still the same. We will be using method of lines. Let me go back to Yeah, so similarly to method of lines, we will be converting these ODEs into set of these PDs into set of ODEs. So we will be doing something like, I let us take +1 delta Z minus K CAI CBI. Like this, we will write equations for all the other points. So we will be getting for each case. for each what shall I say? Shall I say? Yeah. So if I distribute it in, so for example, in 3 elements, so I will have 4 nodes, and for each node, I will have 3 equations, right? CA, CB, CC. So I will have 3 ODEs for each node. In total, I have 4 nodes. So I will have this is for one node, for second node, for third node, and for fourth node. So this will be my entire discretization, and each of these equations will be these, right? So dc by dt, I will write dca by dt as this, dcb by dt as this, and likewise I will continue. The other thing that I can do is that I can write all of my CAs together. So I can write CA1, CA2, CA3, CA4, and then CB1, CB2, CB3, CB4, and like that for CC1 and CC4. Both the cases, I will get the same answer. The only difference will be like how I am writing these equations inside my function. So yeah, so it will be like the equations that I was supposed to write here, 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 I will be writing them together. Okay, so I will just show this. Any doubt in this multivariable case? It will the method is similar to what we were doing earlier. It's just that the equations are coupled now. So we will be converting each of them in as a first order ODE, and then we will be solving it. Okay. The coupling comes from these terms, with like CA is dependent on CB and CC is dependent on CA and CB both. Yeah. So I've assumed some of the variables, they were not given in the problem. So I've assumed like k is equal to 1 and u is equal to 0.5. Length is given to, it's not, yeah, length is also I've assumed L is equal to 1. Discretization, I'm discretizing it for 20 number of points. So my dx would be L by nx. So L is 1, nx is 20. So my dx is 1 by 20. Okay. So I will create this special grid, and then I am solving for these time steps 0, 0.5, 1, 2, 5. Like I'm not solving for these steps. Since I'm using OD 15s, so it will be giving me a solution only for these time steps. It will solve internally for all the time steps in between also, but I will be getting solution in output only for these time steps. So these are my initial conditions. Initially everything is 0. These two are my boundary conditions. So I have taken all my CA together, all my CB together, all my Cs together. So since this is like 20 discretization, so my C naught or my C vector is 60 cross 1 in length, with the first 20 elements belonging to CA, the next 20 elements belonging to CB, and the later like the uh, last 20 elements belonging to CC. So this C01 basically means that my CA 1 is 1.2, and this basically means that my CB 1 is 1, which in this case would be like C0 21 is equal to 1. These are my options for the OD solver. And then here I am solving my solving using OD 15s. So will be going, will be, yeah. So this is my PD system. CA is all the numbers, all the elements of C from 1 to 20. Then from 21 to 40 comes into CB, and then from 41 to 60 comes in CC. Okay. And this is just in initialization of my derivatives, and here I am calculating my derivatives. So I am using a backward difference formula. I can use the forward difference as well, and I can use the central difference as well. Just you need to be make sure that if you are using a forward difference, then at the end node you have to use a backward difference formula. Right now I'm using a for backward difference, so I can go from the second node to nx to all the way to the ns end node using the forward difference formula itself. Okay. Also, like since we saw during the last lecture also, this is like minus u times f of x, right? Minus u times del u by del t, right? So it's like it's against the flow, or is it with the so, yeah, it's with the flow. So when it's with the flow, you need to use you generally a backward difference gives better results as compared to backward difference as compared to forward difference or central difference. We saw that in last week also, like for one problem which was similar in nature, but for a single variable case, we saw that using central difference uh, we were getting oscillations, right? Yeah. But for backward difference, the oscillations were not there. The solution was much more stable. Yeah, so this is these are my terms, my time derivatives, and then I'm combining all the derivatives as a single vector, and it's my output. Okay. Yeah, so I solve this using OD15s. Then I extract the solutions for each series for all the time steps. So CA includes for all the time steps, CV includes for all the time steps, and CC for all the time steps. And then I'm here just plotting for the end time step, that is for t is equal to 5. Okay. I can run this in a loop and I can plot for all the time steps, which is also very simple to do. So for t is equal to I have 5 elements. This will just be t plus, no, not plus 1. This t is fine. Okay, and I will just decrease the line width a little bit. Yeah. So the red one is for CA. The first one is t is equal to 0. T is equal to, I think, 0.5. 5, 0.5, t is equal to 1, t is equal to 2, and then t is equal to 3, t is equal to 5, the last one. Yeah, so this is like for using backward difference. On the same set of ODEs, if I use forward difference, if I use central difference, okay? So x minus 1, c plus 1, c minus 1. This should be using backward difference because we don't have the node. CC, CC, and rest will remain the same. Yeah. So now if I run for this, yeah. So you see the solution becomes unstable. Still unstable. Still unstable. Yeah. So for forward difference, for central difference, the solution becomes unstable. No. Should be next. Next. Yeah. So we get these advective terms and eventually it becomes unstable. So you see, eventually, like initially what was, if I do it for large number of nodes, so initially like for backward difference, I was getting smooth plots for each of them. For central difference, I start to get these oscillations around the point, around those points, right? So this means like for such problems, for these such advective problems, we need to usually generally backward difference is used for these such problems. Central difference gives us these sort of oscillations which should not be present. Okay. So any doubt in this? Okay. Yeah, so then we will solve these uh, two problems. Then we will call it a day. So the first problem is similar to what we have solved initially. We just need to change the function and rest everything will remain the same. Okay. So first we will solve this using analytical derivative, and then we will try to solve this using numerical derivative. So I will use the same code. Just let us use the analytical part. So we just need to change this function. Rest everything will remain the same. And we need to change the initial condition. Okay. So these two things that we need to change. So first I will change the function. So log 1 divided by and for analytical derivative. Okay, I will change the initial guess. Yeah, to 10. Okay. It's a function of t, not x. Yeah. So the solution converged and it converged to a value of 10 to 17.219783. We can check. Uh, so we get a value close to 0. That means the solution is correct. Now let us do the same thing using numerical derivative. I will just change this line because we are calculating the derivative numerically using this function handle itself. So we don't need to create another function. Yeah. So let us do this. So this one, okay, let me screen. This is the value that we are getting using analytical derivative, and this is the value that we are getting using numerical derivative. Yeah. So you see this, since this is like a much more complicated function than the earlier 2 minus x plus log x. So in here we see a little bit of difference, but it's after like after the 8th decimal place. So it's not even the 8th decimal place. It's in the last 2 decimal places, right? So we are getting pretty much the same result using both the methods. Now, if I reduce this tolerance, then I think we might, yeah. So as we start to reduce the tolerance, so we get, so the solution starts to diverge from the analytical part, but still it's like, still it's it's closer to the true solution for a respectable number of decimal places. Still, it's close to the analytical solutions. That shows us that how robust Newton-Raphson method is, especially for single variable cases. For multivariable cases also, it will converge, but for such small, like for such loose tolerances, the results will not be closer to analytical Jacobians. Okay. So usually the tolerances should be in the range of 10 to the power minus 6, minus 7, 5, in that range only. But for a single variable, you can see that it is still the results, it's a respectable result. Fine. Any doubt in this part? Okay, then let us go to the last problem and then we will finish it. Yeah, so this is, we need to find the volume of solid of revolution for all of the x points. So if I plot these points, so they are something like at x is equal to 0, it's 5, then 5.5, then 6, then 6.75, then 6.25, then 5.5, and then 4. So the solid is something like this. Okay. So yeah, I will revolve it in 3D. So we need to find the volume of this revolution. Okay. Now, how do we do this? One way would be to, yeah, the one way would be to calculate the area of this circle, then calculate the area of this circle. Like we calculate area of each of these circles. So we get a mid, no, we get a vector of all the areas. Like in here we get a vector of all the areas for all the x values, and then we use any of the either the trapezoidal rule or Simpson's rule to uh, to get the volume of this entire thing, right? That is what we do with trapezoidal, right? We have a function, we have a function value at a point, and then we integrate that entire value from one point to another point. So we have the area values at all of these points. So we have the area values at all of these x values, and we interpolate that area to get volume, right? So volume would be just area as a function of x dx, right? From x is equal to 0 to x is equal to 15. Now, what we are doing over here is that we are calculating this area like as a simplified expression of pi d square, and we are doing this. The other thing that we can do is the one thing that we can do is we can do interpolation between these points to get these areas at a lot of these midpoints, and then we can do much better approximation of the volume. And the other thing that we can do is we can fit a curve through this entire set of points, and then we use that curve to approximate the radius at infinitely many points, and then we do, yeah, so basically we are doing interpolation there also, but we are fitting a curve and then we are finding the points based on that curve. So we are doing regression first, then we are doing integration. The one way is what we are doing right now, just directly calculate the areas, use the trapezoidal rule. Another way is to do interpolation between the points, then use the trapezoidal rule. And the final way is to use a regression model to fit a curve through this data, and then using that regression model to calculate the area, right? So that will be like we can, if we fit a regression model to this curve, then we can get a analytical representation of this a to the this curve function ax, right? What is this ax? Ax is nothing but pi r square, right? Now, if we get an analytical or we get a polynomial representation of this r, then we get a continuous function for ax, right? And then we can simply use the integral function of MATLAB, the inbuilt integral function of MATLAB to calculate this volume. Okay. So we will look at those two approaches. Any doubt in this, like what in the three approaches that we can take? First one is interpolation. The first one is using simple trapezoidal or Simpson's rule. The second one is using interpolation, and then the third one is using regression. Okay. Fine. So this is our data set. Yeah. N is just the number of points in the data set. I am right now I'm trying to fit a cubic polynomial to this data. So I have created this matrix. Here I can write N. So first one is just a column vector of ones. Then it's x values, then x square values, and then x cube values. Okay. And then this is my least square solution for the coefficients. I'm extracting the coefficients here. A3, A2, A1, A0. A3, A2, A1, A0. So A3 would be the last coefficient, and likewise it depends, like basically it depends how you are creating this X matrix. If I replace the order of these X matrix, then this order will also be replaced, right? It will also be reversed. Then this is just a, I'm creating a fine grid for smoothing, for the plotting a smooth curve. So D is the third order fit. So this is my define, and then I'm plotting over here. So I will first run until this part. So this is the data. And these are my data points, and this is a third order curve fitted through that data. Okay. So even though like in here we are losing some volume, right? So actually it would be much better since there it's like a change in slope, very rapid. There is a very rapid change in slope over here. So it would be like a much better idea to fit two curves through this. So like we can divide this over here, and then we can sort of fit a quadratic curve over here, and then linear or a quadratic curve over here, right? So that will like right now we are losing a part of volume over here due to this cubic fitting, right? So So yeah, in the next part, I'm calculating my radius squared. So this is just my r square that I'm calculating based on these coefficients that I got. So this is my radius for the yeah. So this is like a function handle that I have created over here, right? Uh, so a function handle for r square where my r is a cubic polynomial. Okay. Then I'm just using the inbuilt integral function of MATLAB. So this integral function will give me a integration of r square dx from x is equal to 0 to x is equal to what is x and 15. Okay. And I'm multiplying it by pi to get my volume. Fine. Any doubt in this integral function? I just need to pass a function handle of what I want to integrate and both the end points, like the initial point and the end point. Then I'm also calculating it using the trapezoidal method. So I get this vector of all the area values. So pi d by 2 whole square. And then I use the trapezoidal function on this x and a values to get my volume using the trapezoidal method. Okay. So if I run this entire thing, just yeah. So using solid of revolution, we get a volume of 400.1074, and using trapezoid method, we get a volume of 395.8898. We can also fit a second order curve and see what value we are getting. Also, we can do the same thing using Simpson's 1/3 or 3/8 rule to get the to get an estimate of the volume. Okay. Yeah. So this is like this is the problem where we used integral function along with the curve fitting, right? Okay. So any doubt in this? Any doubt in journal that you guys have for any of the in like not only in today's lecture, any of the thing related to exam also or the syllabus till week 9? Okay, then we will end this lecture. All the best for your exam. Okay. Good night, everyone.